So today we're going to talk graph theory. And let's see. Where are we? So hopefully we'll get, we're going to start with graph theory, and we'll show how linear algebra actually connects to that and to actually solve some graph problems. And then hopefully we'll get to spend a little bit of time on Markov processes. If we don't get very far with that, we'll actually continue with that on Monday. So those of you who are watching this after Monday's class probably makes a lot more sense if you had done this in the other order. So, applications of linear algebra. There are lots of kinds of things that we can do with linear algebra, which is why we're studying it. And computer vision and all sorts of computer graphics involve a lot of manipulation of the images, which involves a lot of transforms, most of which are linear transforms of the kinds we've already studied. So there are many different real-world applications of linear algebra, but the one we're going to talk about today is graph theory. So the first question is, what's a graph? Well, you've probably seen things like this, and this is a graph of a cubic function, f of x cubed something or the other. This can also be called a plot. You probably learned in your basic mathematics classes, in high school, algebra or whatever, that this is a graph. Well, that's a graph. These are different kinds of graphs. Maybe you've seen 3D graphs. All of these are not the kind of graph we're going to talk about today. I sometimes call those graphs, but I often call those plots, like I said. But in any case, the word graph has multiple meanings out in the real world, one of which is a definition that actually looks like this in terms of words. So it's this structure where you have a set of objects and you have relationships between those objects, and those relationships can be described as some sort of link between these objects, and we can call those links nodes or vertices. So you'll often hear the term vertex and edge, or node and link will be the pairs of terms that are often used to describe this structure. So it looks often like this. So these are two representations of two different graphs. The one on the left has 6 nodes or vertices in it, and 1, 2, 3, 4, 5, 6, 7 edges or links in it. And the one on the right has 4 nodes and 1, 2, 3, 4, 5 edges or links. What do you see as the difference between the one on the left and the one on the right? Mordishta, what's the difference between the one on the left and the one on the right?
Different?
Yeah.
The left graph didn't have the vector.
The left one, what?
Don't have the vector.
Yeah, the left one doesn't have arrows. Right?
Oh, yes.
These arrows and the one on the right, they establish a direction for the link. So we call the one on the left an undirected graph, and the one on the right a directed graph. So let's see. I already told you briefly here that the circles here, we call those nodes or vertexes, and then the lines that actually connect to those, we call those edges. And the one on the right in this case is the undirected graph, and the one on the left is the directed graph. Now the question is, how do we actually write down these graphs? There must be some way of actually drawing them. Or write down in the information that actually governs that describes the structure of that graph. Well, there are a couple of different ways. We can describe, generally speaking, we describe a graph in terms of 2 sets. One set is the set of vertices and the other set is the set of edges. So in this case, got a picture of the entire structure of my research group up here on the left. Ooh, I soon wants a picture on the whiteboard up here. This is from a discussion I was having with somebody here on Thursday. You can share that with people if you want. These black markers don't erase as well. The black. So a graph, we'll often use the letter G, and we'll write it like this. Just, the graph is described as V and E. Man, that's not going to be legible while I'm sharing the screen, is it? That's all right. We'll see it come up again later. So in this case, the graph that's actually shown in your video here or on the screen consists of six nodes: red, green, blue, orange, purple, and brown. And then the edges are as written there in that list. So an edge can be defined as a pair of nodes that have some relationship, or a pair of vertices that have some relationship. So you see the first one, that's listed there is red, blue. So there's an edge connecting red, blue. How many of these could there be? If we assume that there's only one edge between any pair of nodes, and that there are no self edges, there are no edges that go back that start at, for example, the node red and then come back to the node red. What's the maximum number of edges we could have in this? Mia, what's the maximum number of edges we could have in our graph as a function of the number of vertices? Let's see, somebody put something here in the chat. 4, all right. 4 edges. Let's see. Let's take this graph. 1, 2, 3, 4, 5, 6, and we have this. Let's see, is this right? Whoops, no edge there. Yep. Is that all of them? Yeah, that's all of them. So at the moment we have 1, 2, 3, 4, 5, 6, 7 edges, and we have 6 vertices. We see blue, brown, orange, red, green, and purple. So how many more edges could we add to this if we were adding edges? What's missing? Well, let's see. We could add green to purple here. We could add green to orange, green to blue, green to brown. All right, let's see. What else do we have? If we take the red one, we could still have red to brown, and I think that's all. Let's see. Blue could still be connected to brown and to purple. And let's see, and it's already connected to green here. I guess that's all for that one. What are we still missing here?
Green.
Right, purple to brown. And let's see. I think that's everything. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 edges total. We got 15 edges total here in this graph. These are a little hard to see, maybe a photo. It's actually convenient having you here. So, one of the ways in which we can write this, we can write the size of the set. We have the set V. So V is this set blue, brown, orange, red, green, purple. What we can write is we write what's the right term for that? Magnitude of V, or the amplitude of V. The size of the set V would be 6. There are 6 total elements in this set. The original set E, the set that was written here in black, the value of the set E was, we had 7 original edges. And if we call the set E prime here, if we call that all our edges, then we had a total of 15. So let's see. So Aman says n times n minus 1 over 2. Hey, that kind of makes sense, doesn't it? Let's see. So if we say, let's call n, let's call our the size of our set V, let's call that n. And if you count the n nodes, well, from each one of the nodes, it can be connected to n minus 1 other partners, right? So that would be n times n minus 1. And in each case, in this case, every edge is symmetric and it's counted twice because we're dealing with undirected edges here. So yes, then it would be divided by 2. So the maximum number of edges and the size of our system here, the size of our total number here is n times n minus 1 over 2. That's the maximum, right? So we're going to talk a little bit more about these things as we go. Let me go back to sharing my screen here. All right. One way we can write down this this overall structure is what we call an adjacency list. So for 2 nodes to be adjacent in a graph means that they are, another word for this is neighbors. So in this case, with the original graph as drawn here, A has as neighbors or as adjacencies, A is connected to the nodes B, D, E, and C. So you can see A is connected to B, C, D, and E in the list there. B is connected only to A and D. C is connected only to A. And you can write out the total structure of the graph this way. Another way to write it out is what we would call an adjacency matrix. And the adjacency matrix, for the moment, we're going to assume that the entries in this are always either 0 or 1. In a formal adjacency matrix, that's what we actually, they're always just that. It just says that these are either neighbors or not. But there are, other advanced structures for graphs where the edges have values that aren't just 1, and we'll talk about those I think on Monday. I don't think we'll get that far today. All right, so we can write this graph where we can write out the structure of this graph using this data structure called an adjacency matrix, where the matrix is square and it has as many rows and as many columns as there are nodes in our system. So it's an n by n matrix for n, and n in this case equals 6. So the columns A through F, and then the rows A through F, and their entries 1 where the two nodes are connected and 0 where they're not. So for the edge AD there, you can see that A is connected to D, and it's circled in the matrix there. But this is, in this structure that we have here, this is written in what we call row major form. So A is connected to D. This row major form is what we use mostly in graph theory. And you can see in this case that A is connected to D, but also D is connected to A. And so we've circled the one there in the top row, but if you look in the left-hand column, there's also a 1 in that same place in the column, because these edges are symmetric. So if A is connected to D, then D is connected to A. But in the case of a directed graph, we need to be a little bit more careful. So in this case, A is connected to B. Whoops, let's see. Here we go. Let's stick with this. A is connected to B, and so if the first row is A, then the first column is B, and the first column is A, the second column is B. You'll see that that first row contains a 1 only in the column corresponding to B, because that's the only node that A has an edge going from A to that node. So A to B means that we have a 1 in the row labeled A and in the column labeled B. Notice that that means that there's not an equivalent one from B to A, because there's no arrow connecting B to A. And so if you look in row B and column A, that's the left-hand column, the second row, that's a 0 because there's no equivalent edge connecting there in that direction. So for this directed graph in this adjacency matrix, let's see, in this particular structure, we have 1, 2, 3, 4, 5 edges. And if you look at the matrix, we have 1, 2, 3, 4, 5 ones in the matrix, and everything else is 0s. Whereas in the undirected graph case, let's see here, in this case, as we said, we've got 7 edges in this. And if you count the total number of ones here, we got 4, 6, 7, 11, 13, 14. We have 14 ones in this matrix, because each edge shows up twice in this, in the undirected form of the adjacency matrix. Any questions on the adjacency matrices so far? Everybody's happy with those? So as it noted on the slide here, because we're talking about the origin and the destination of this directed edge going from A to B, as written here, this is row major format for the adjacency matrix, where the row represents the origin of the edge, and the column represents the destination of the edge. This would be the column major form of the same thing, where going from A to B, instead it would be in the A column and the B row. So from going, the column represents the from, and the row represents the to. So those two matrices, how are these related? What's the relationship between these two matrices? Aman, what's the relationship between these two matrices?
Let's see.
They're not the same matrix, right?
Yes, they're not. Yeah.
But what are they? One of them is the something of the other.
Let's see.
Just looking at the shape, what do you see about the shape, or where the entries are? Do you see a pattern here?
I'm trying to look for a pattern, but
So we have the row major and the column major. And then the two of them together, they're almost the same, except that everything's flipped across the diagonal, right?
Oh,
So things that were rows have now become columns.
yes. Yeah, I can see that. Yeah.
So what do we call that?
Is it transpose?
Bingo, it's the transpose. So this is the transpose one of these matrices is the transpose of the other. Actually, because transpose is a symmetric operation, they are each the transpose of the other. All right. That was the adjacency matrix where we have one row and column for each node in the graph, or each vertex in the graph. The other way we can describe the same thing is what's called the incidence matrix, where instead we have the we describe both the nodes and the edges. So in this case, you have one column for each node and one row for each edge. So in the diagram there on the right, E1, E2, E3, and E4. So we have four edges. And so we have four rows, and each one of the columns, 1, 2, 3, 4, corresponds to one of the vertices. So the size of our matrix in this case is the number of edges by the number of rows, or actually the other way around. Let's see. Rows first. So it would be the number of edges by the number of vertices would be the size of the matrix. So if you add an edge to this, you need to add a row to the actual column, or a row to the actual matrix. And so this gets a little bigger. This is a different way of actually writing down the structure of the graph, and it has uses, but most of the time we'll actually be using the adjacency matrix. So let's see, any questions about these representations for graphs? Either we had the adjacency list, which is a very common structure to use in software if you are writing code that deals with a large graph. But the adjacency matrix is also a very common way to do things. You have to write things down if you need to actually calculate particular characteristics of the graph. So any questions about this? Either the adjacency matrix, the adjacency list, the adjacency matrix, or the incidence matrix? Everybody's happy with this. All right. So what can we actually use this for? Well, one of the things we can use graphs for is to model relationships between objects, where these objects might be a person or a thing or an activity or something. Right? So you can see that in this case, there's a person there in the middle whose name I don't know, although this was taken, this is probably a mocked up thing, and this particular figure was taken from the website Business Insiders. But this person here in the middle, she has two friends who are connected there above and below her with an edge labeled with the type of relationship. It's labeled as a friend. And she likes to listen to Spotify, and she likes to cook. So that's connected to, I guess that's a cookie. I guess that's cookies she's making. And then she likes to watch Netflix. So we can write down these relationships in a graph structure. We can also write this down, just thinking of the relationships between people, using or in what's called a social graph, the social graph. And you may actually hear that term, particularly with respect to Facebook. For some reason or other, the word seems to get applied to Facebook more than to other social networking services, but the concept is general. The idea is that everybody has a set of people they know, and so people are vertices in a graph of the population on the whole planet, and edges are the relationship between people who know each other. There's a really famous concept that goes back. It's described in this book from 1990 called 6 Degrees of Separation, but the concept actually goes back much farther. And the idea is that you could have the graph of connections here that connects everybody on the planet, that between any two people on the planet, the longest distance, but the shortest connection between any two people on the planet is always either 6 or fewer people. So I don't know Joe Biden. I don't know the president of the United States, but if I needed to send a letter to Joe Biden and it needed to go person to person in order to get there, well, as it happens, a friend of mine who got married about 10 years ago. Man, that's a terrible example because she actually died a couple months ago. It's terrible. A good friend of mine who died recently, and she actually went to law school with the husband of the United States Vice President, Kamala Harris. So I know my friend Molly, she knows the husband of the vice president, and the husband of the vice president definitely knows Joe Biden. So it could have gone from me to Molly to her friend to the vice president. That would be 3 hops to get from or to the president. That would be 3 hops to get from me to the president of the United States. If I needed to get something to the emperor of Japan, right? Well, our professor Jun Murai, who I spend a lot of time working with, he's met the emperor, right? I could go 2 hops from here to the emperor. I'm not sure Jun and the emperor are actually good friends, but you know, right? As a principle, the two of them are connected. So 2 hops to the president, to the emperor of Japan, or three hops to the president of the United States. That kind of connection, and the assertion in this book 6 Degrees of Separation is that the maximum shortest path between two people is on the planet is just 6 hops. It's a fascinating idea, very difficult to prove, but there's actually some data on this. And this data comes from Facebook research. I said that Facebook often gets named in the context of this network graph because they are the largest social networking service on the planet, and they have enormous amounts of data that they collect about everybody on the planet. So they have taken this set of statistics. I'm not actually sure what year this research was actually published, but what you're seeing here is the distribution of the average number of steps it takes to get from each individual on Facebook to every other individual on Facebook. So the average here was 3.57 steps. So from you, who are probably a Facebook user, because it turns out that the majority of the people on the planet have a Facebook account, whether or not they're regular users or not. The average distance from you to anyone else on Facebook is 3.57 steps. And you can see from this graph that it's kind of asymmetric, and it's a little bit of a long tail to the right, but even that doesn't actually go very far. And it turns out that almost everybody is less than 5 steps away. So this kind of analysis tells us various things about how information can propagate. A common concern over recent years has been the propagation of misinformation or disinformation about, for example, vaccines and the climate and US politics and things like that. There's a whole lot of mis and disinformation out there in the world, some of which is deliberate, and a lot of it is shared person to person. So you can look at this kind of graph and understand how information actually propagates. Also, what have we been doing for the last 3.5 years? For most of the last 3.5 years, we were sitting at home, right? Why? Because of the COVID-19 pandemic. And so you can create a graph that shows the physical interactions with people, and that set of physical interactions with people can help you understand how diseases like COVID-19 actually propagate from person to person, or how they propagate within a community. There was a lot of that graph structure-based research early on in the pandemic, trying to model how the virus would actually spread within communities. And a noticeable chunk of that was really kind of naive. It didn't fully capture everything about the social interactions and the probabilities of people catching diseases from each other. But it was headed in the right direction, but the models weren't realistic enough to produce very good understandings of how it was going to actually propagate. So in that sense, for me, as a big advocate and a big fan of the mathematics of graph theory, it was a little bit disappointing. It turned out that much simpler mathematical models actually did a better job of actually representing what happened in the real world, in terms of how quickly the number of people who were infected grew, both globally and within individual communities. If you were representing that propagation from person to person as a graph, would you use a directed graph or an undirected graph? What do you think? What do you think? Would you use a directed graph or an undirected graph for the propagation of a disease?
One more time, please.
Sorry, say that again?
One more time, please.
So to represent people getting sick from each other, we can represent that as a graph. Soon got sick and made me sick. So would we represent that as a directed graph or an undirected graph?
That direct graph?
Yeah, that's right. We would use it as a directed graph. So Soon's here, so I'm going to pick on Soon. So Soon made me sick, and he made Mia sick, and I made Morishita sick. We can write this out as a graph. Maybe I also made Aman sick, right? In this case, it goes from one person to another, and we would represent that as a directed graph. Let's see. I don't remember if it's actually in the slides later or not, but I might as well cover this particular concept right here and now. This particular structure, notice that I've drawn it essentially with layers going this way. This particular data structure has a name, this type of graph. This type of graph is what we call a tree. In this tree, you move from one node, a node is called the root. And then from the root, you can move toward other nodes in the graph, and eventually you get to nodes that have nowhere else to go below them, and those are called leaf nodes. So Mia and Mordista and Aman are leaf nodes in this graph. Soon is the root. I am an interior node within the tree. Trees can be composed of either directed or undirected edges. It can be either a directed or an undirected graph. In this case, it's a directed graph. If it's a directed graph, there's always one root for doing this. This is a directed graph tree, or a directed tree. All right, picture. But if we take the arrows off of this and just connect them, then now it is an undirected graph. Picture. And once it's an undirected graph or an undirected tree, there's actually something interesting about this. I have labeled soon the root, but is soon necessarily the root here? Well, in an undirected graph, as a tree graph, any of the nodes can be the root. So we can move Mia up here. And now this is still a tree. It's still a tree structure, but we've now declared a different root, but the graph itself has not actually changed. Okay. In this case, what we call the depth of the tree. So this would be depth 1, 2, 3. 1, 2, 3 in this case, and those are that's another way of drawing the same tree structure, the same graph. So we can draw the graph itself. The data structure does not change just because we drew it a different way, but there are times in doing different kinds of graph analysis where we might want to declare a particular node to be the root of the tree overall for some particular evaluation purposes. Did you post that one yet? Oh, I forgot to unshare the screen there briefly. All right, you all can see the graph there, and Soon's also posting photos of this on the Slack. All right. That was a little bit of a side step there, or side discussion. Let's go back to the main line here, but these concepts will come back up again later. Oh, wait, hang on. I forgot to tell you about the most interesting characteristic of a tree. What's different between this and the graph that we had earlier? Well, in this case, there are no loops. No loops. In the previous structure that we had, or in any simple structure, if you have 3 edges that are connected there, we would say that this structure has a loop. So this has a loop. So it's therefore it's not a tree. by definition. We're going to talk a little bit more in a few minutes about the number of edges and what the difference is between having one tree and having more than one tree in your particular graph. So we'll come back to that later. All right. Another use for this is modeling computer networks. And I'm a computer engineer. You all know that. Computer engineers, we often learn two things about graphs in an ordinary computing or ordinary networking, computer networking kind of context. One is how to find the shortest path in a complicated network, and the other is the notion of what we call a spanning tree. And we'll talk about spanning trees at some point, although we may not get to that until Monday. This is an interesting one. This is one of the most famous problems. Well, it's probably the most famous problem in graph theory. You all know Euler, right? We use Euler's equation frequently, right? E to the I pi minus plus 1 equals 0. Yeah, you already said. So that's Euler's formula. Stop sharing that again so you all can see this. In Euler, so this is Euler's formula, but Euler also created one of the most interesting and original graph theory problems, and this was all the way back in the year 1736. If you have a city with 7 bridges, in this case, a town named Königsberg. The question is, can you, on a walking tour of the city, cross all 7 bridges exactly once? So if we draw this as a graph, it's in the slides, but I'll show you. I might as well go ahead and do it here. So we've got the island, North Shore. We're going to describe each one of these geographic portions of the area using a node. East Shore and the South Shore. Is that right? Is that everything? 1, 2, 3, 4 areas. Now, in this case, we're going to describe each bridge using an edge in our graph, but in this case, we're going to allow there to actually be multiple edges between these nodes. So we can do this. North is connected to east via one bridge. East is connected to the island via one bridge. East is connected to south via one bridge. And south is connected to the island via 2 bridges. Let's see. So we should have 7 bridges. 1, 2, 3, 4, 5, 6, 7. Now the question is, can we start anywhere on this graph and find a path that walking around the city would take us across all 7 bridges exactly once? What do you think? Is that possible? Maybe we'll start at the island. We'll go north across, we'll go across one of the bridges to the north. And then maybe we'll go to the east. And then maybe we'll go to the south. Okay. What do you think? That's taking us someplace. Can we complete this tour and find a path that takes us across each edge or across each bridge exactly once? What do you think? Can we do a poll here? What do we do? What happens if we do a poll? Choice one, let's see. Oilers. We can cross all 7 bridges once. Choice one would be yes, and choice two would be no. And choice three would be maybe. Launch the poll. What do you all think? Soon you get a vote on this too. Mia, I'm on Morishita. Give me a vote there. What do you think? I've got 2 votes so far, 3 votes so far. Still waiting on 1 vote here. Still thinking or away from keyboard? All right. Somebody hasn't voted. You voted? So one of the other students didn't vote. Everybody said no. Everybody who voted anyway. All right. It turns out you are correct. There's no way to actually get across all 7 of these bridges going exactly once. All right, let's see. So we represented this as this graph. Hey, what a surprise. The graph looks exactly the way I drew it. How nice. How can we solve this, or how can we prove this? Actually, not sure if this particular set of slides takes us directly to that solution or not. Okay. But one of the things we can talk about here, the next thing we're going to talk about, is a way to represent walking on a graph or moving from one node to another on a graph. So let's say we start at the node B, assuming this is row major form here. So if you look at the row labeled B, it has 1s in the columns A and D. That means we can move from either B to A or D. So at time 0, we are at B. At time 1, we can be only at A or D. Those are the only 2 places we can end up. If we take 2 steps, we can go from B to A and then back to B, or we can go from B to A to C, or we can go from B to A to D, or this whole set of things. There's a partial list there on the left. Now what? These entries in this adjacency matrix, one of the reasons that these are 1s in this adjacency matrix is that if you look at the number in that, it tells you how many steps away each one of the other nodes is, except that 0 in this case means we don't have any way to get there yet. So to get from A to B is 1 step. To get from B to A is 1 step. So the entries in the adjacency matrix can be viewed as actually referring to a path of length 1. Now, using this adjacency matrix, is there a way we can find all of the length 2 paths out of this, or all of the source and destination pairs, all of the starting points and ending points we can follow to get from any given point to any other given point in 2 steps. What do you think? Any way to get there? Mia, what would you do with this in order to get to find all the possible source destination pairs of over 2 steps? What do you think? Any bright ideas? My pocket is continuing to buzz, and I don't think that was soon. I guess it was. Let's see. In the chat we have no ideas from mine. Okay. How about we do this? If the matrix, the adjacency matrix represents where you can get in 1 step, then if we apply that operation twice, then that will tell us where we can get in 2 steps. And the way we can do this is by multiplying the matrix by itself, or squaring the matrix. So what's the outcome of that going to be? Let's look at a smaller graph so we don't have to do all of this together. We don't have to multiply all of that out by hand. This graph ABC there on the left, there are 2 links in it. So if you look at the adjacency matrix, there are 4 ones, divide by 2. There are two links in this. A is connected to B and C. B is connected only to A, and C is connected only to A. So the number of paths of length 2, you can go from A to B and then back to A, or you can go from C to A to B, and there are exactly 6 2-hop paths, 2-hop approaches to this, or 2-step paths. Is that right? Yeah, I think so. I think that's everything. We squared the matrix here. And what does this tell us? Well, to get from A back to A, the one way we can do this is by going from A to C and then back to A. The other way we can get there is by going from A to B and back to A. So if you look at the lower graph, that 2 in the upper left-hand corner there, that's the AA entry in the matrix. So what we have done, and that's a 2, right? That means that there are 2 possible paths that start at A and end at A. 2 possible 2-step paths that start at A and end at A. Okay. Notice that everything else in that row is 0. There is no 2-step path that starts at A and ends at B. So that entry is 0. There's no path that starts at A, goes 2 steps and ends at C, because we're assuming that in every step you must move along one of these edges. So you can't go from B to A, or from A to B and then just wait at B, because there's no edge that connects B to itself in this particular structure. So on the second step, once you're at B, then your only choice is to go back to A. So to get from A to B, we can do that in 1 step, but we can't do that in 2 steps. There's no way to, there's no path of length 2 that starts at B, that starts at A and ends at B, and conversely that starts at B and ends at A. But if you look at the BB entry, which is the one there in the middle, there's exactly 1 2-step path that starts at B and ends at B, and that would be BAB. If you look at to its right at the one on the right-hand side of the middle row, that would be a path that starts at B and ends at C. So the way we start at B and end at C in 2 steps, you go B, A, B, 2 steps. So each one of these entries in this matrix tells us how many different paths there are that start at a particular node and go n steps and then end at a particular node. So for A to the n. You're taking this, multiplying it out, you can see the multiplication structure there, where each application of this matrix represents one step in your walk through this graph. And we can redo this for any arbitrary n. So if you want to start at A and find out all of the places you could end up after 10 steps, you would take this matrix and you would calculate A to the 10th, and it would show you how many different paths there are to get from A to B in 10 steps, or A to C in 10 steps, or what have you. This is a little bit surprising or a little bit tricky. It's probably a new concept. So what questions do you all have about this at this point? Questions about computing these paths in a graph by multiplying out the matrix? Here's a question for you, which I don't think is actually covered in the slides. Let's see. Let me do a slight. I don't want to do the whole 6 by 6, but let me do a slightly bigger graph here. A, B, C, D. Let's do this. What's our adjacency matrix A for this? Starters, it's got to be 4 by 4. Let me make that a little bit bigger. Since we've got 4 nodes and we're doing the adjacency matrix here, right? A, B, C. They actually use the squares on this board. Why not? A, B, C, D. A, B, C, D. Is there a connection from A to A? No, so that's a 0, right? From A to B, yes. From A to C, yes. From A, oh, let me stop sharing my screen again. From A to D, no. From B to A, yes. B to B, no. B to C, yes. And B to D, yes. C to A, yes. C to B, yes. C to C, no. And C to D, yes. And D to A, no. D to B, yes. D to C, yes. And D to D, no. What do we get if we square this matrix? If we count the number of 2-hop paths? Let's see. Let's calculate that by hand, actually. Right? A squared equals 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, and 0, 1, 1, 0 again. Right? Yeah. Times same thing, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, and 0, 1, 1, 0. What does that equal? Let's see. Multiply the first row times the first column. That's going to get us 2, isn't it? First row times the second column gets us 1. First row times the third column gets us 1, and times the fourth column gets us 2. Second one gets us 1, 3, right? And then 2, and then 1 again, and then 1, 2, 3, 1, and then 2, 1, 1, 2. Do I do that right?
I think so. Yeah.
All right. This means, again, if these are A, B, C, and D, A, B, C, and D. Now, interestingly, so this tells us that there are 2 paths that start at A and that come back to A after 2 steps. So you can go A to B, A, C, A. That'll take us there. Right? Starting at B and ending at B, there are actually 3. BAB, BCB, BDB. Okay. Starting at B and ending at D after 2 steps, there's exactly 1 path, B to C to D. That's the only way to get there. Good. Now, let's see. A photo, I guess, of this. Get the whole board from the. Now, one of the things we can do that we haven't yet described, but will come up later when we talk about Markov chains, is how to actually apply this to something that describes your current position. So if we take the vector x and have that be our position, so x equals, write this, or should I write this? Write this over here. X equals 1, 0, 0, 0. That means that we started in position A. Sorry, my apologies here. We're using the capital letter A, both to represent the adjacency matrix and to represent the first node in this graph. That's actually probably a poor choice. Should have been a little more careful about that. But where can we get to after 2 steps? We can take this vector and multiply it by that matrix. Okay. So if we take AX, that will be 2, 1, 1, 2, 1, 3, 2, 1, 1, 2, 3, 1, 2, 1, 1, 2. And if we multiply by 1, 0, 0, 0, what do we get?
This is A squared, right?
Oh, yeah, right. Sorry, that's correct. This is A squared. What do we get? What are the 4 entries that should go in this vector?
2, 1, 1, 2.
Bingo, 2, 1, 1, 2. Multiply 2 and 1 and then 1 and then 2. That's a 2, 7. So that tells us that there are 2 A to A paths, 1 A to B path, and 1. Let's see, so that would be that. Move this down here. 1 A to C path, and 2 A to D paths on this particular on this particular graph, okay? Does that make sense? Let's see. Two ways to get to A, we said A, B, A, C, A. One to get from A to B. The only way to get from A to B in exactly 2 steps, not 2 or less, but exactly 2 steps. The only way to get there is A, C, B, okay? Likewise, the only way to get to C is A, B, C. And how can we get to D? A, B, D, or A, C, D? We'll see more of that when we talk more about Markov processes as we go on. Any questions about that? How are we doing time-wise here? All right, we've already used over an hour, haven't we? There's still a lot of slides to cover. All right. Next question. Here's a question about your graph. This graph that we did earlier, not the one on the board, but the one that's on your screen right now. How many triangles are there on this graph? Morningstar, you back with us? How many triangles are there in this graph?
1 or 2.
2. I see 2 triangles in this. Yeah, the red triangle and the blue triangle. Well, the AD edge needs to be drawn in both red and blue. So there are 2 triangles. Can we count this without drawing all of these pictures and then figuring out how many red and how many blue and how many green triangles we've got and actually literally counting them by drawing this all out? Well, this is actually really interesting. A triangle has 3 sides. Is there any relationship to a path of length 3? Well, a triangle would be a path where you start at some node X, and after 3 steps, you end up back exactly at X. So take a look, for example, at the ABD triangle there. So if you start at A, you can go A, B, D, and then back to A. And in a path of exactly 3 steps, you've gotten back to A. So that tells us something there, doesn't it? But there are actually 6 different ways in which we could actually 6 different ways in which you could walk on that triangle and end up back where you started. You can go ABDA, or you can go ADBA in the opposite direction around the circle, around the graph. Around the triangle. I'll get the word here in a second. Or as written in orange there, you can start at B. These colors should have matched the colors in the nodes, but they don't. Or you can start at B and go BADB, BDAB, or you can start at D and do it. So there are actually 6 different ways in which you can go around a triangle on this. So if we count the number of those paths, if we count all of those, then in order to count the triangles, we actually have to divide our total by 6. Now, how can we figure out how many paths there are starting at a particular node and ending at a particular node using the adjacency matrix for 3 steps? We did this. To count paths of length 3, we take our adjacency matrix A there and we cube it. A to the 3rd it counts the number of paths on a particular on the graph here. But we have to divide by 6 because we've got to take into account all of the 6 possible paths we're talking about here. But the entries on the diagonal of the graph are paths that start at A and end at A, or start at B and end at B, or start at C and end at C. So each of these paths for the triangle is going to be represented there. So let's see. I thought we actually had the cube of this written out, but we don't. So the trace. Remember that the trace is as written there in the equation. So you've got capital sigma there. That's the sum of a cubed sub I. So that's the row and column within A. That's the things that are on the diagonal, and the sum of things that are on the diagonal is what we call the trace of the trace of the matrix. Right. So we take the trace of the matrix for A cubed, the cube of the adjacency matrix, and then take the trace of that and divide by 6, and you'll get the number of triangles in the overall system. Fascinating, right? Let's see. This paper. My PhD student, Sarah Metwally, wrote this interesting paper about quantum computing. And in this, we're looking at the K-clique problem, or a generalization of that. And we can talk about what the relationship is between a clique and other things a little bit later. You all might want to take a look at that if you want. So in this case, we would end up with, even though I don't have it written out here, the cube of A here would end up with the trace of that being a total of 12, because we have 2 triangles in this, and divide by 6 and you get 2. So can we do the same thing for a 4 cycle or a 5 cycle, meaning a square or a pentagon? Can we count the number of squares or pentagons on a graph using the same thing? What do you think? Aman, what do you think? Could we use this same technique to count the number of squares on a graph?
I don't think so, no.
Why not?
Let's see. A, B, C. Oh, so 1, 2, 3, 4. Oh, yes, you can use it.
You think so?
Yes, but it has to be like, you shouldn't add more letters. Like, it should be the same letters over and over again, like to draw the path. Same like the triangle one.
Same like the triangle. Let's see. So let's take this. I'll write this out here. Let's go with let's calculate A to the 4th. 2, 1, 1, 2, 1, 3, 2, 1, 1, 2, 3, 1, 2, 1, 1, 2. So this will be A to the 4th equals A squared, right? So let's see, if we calculate this out, 10, right? And 9, right? And 9 and 10. And then once again, 9 and let's see, this time. I think 15, if I just did that right. And 14 and 9, if I did that right. And then symmetrically 9, 14, 15, 9, and 10, 9, 9, 10, if I did this right. So in this case, trace of a to the 4th equals what? Somebody should double check my arithmetic on multiplying that out, but I think I'm pretty right. I think I'm right. So what's the trace of this matrix? Marty, what's the trace of this matrix? $40, bingo. 10 plus 15 plus 15 plus 10. No. How about 50? Close. Close. When I did it the first time too, I actually got 40 in my own head too. So you and I made the same mistake. So 50. All right. Let's see. I can't get all of this on the board. On the let's see. How many squares do we have on this figure though? On this graph? I only see one. I only see one. Bummer. So I'm on we tried to count the number of squares using this, but we didn't, right? Or maybe we just haven't figured out how to adjust this yet. Well, let's see. Maybe we haven't figured out how to adjust this yet. So if you started at A and you went B, C, D, and back to A, let's see. That's one path, or you can start at B. So you can start at any one of these 4. So that's 4, or we can go in the opposite direction and you can start at any one of those. So we would need to divide by 8. Except we're still not quite there yet, are we? Because 50 doesn't divide by 8. So what do we have to do? Well, the problem is that there are actually multiple ways in which you can start at A and end back at A after 4 time steps, because you could actually go A, B, B, A, B, B, A, and end up back there, couldn't you? That's one way to do it. Or you could go obviously AC that way, or you could go A, B, B, A, C, B, C, A, and that's a separate way of getting there. So it turns out that you could do this, but you have to account for all of those other possible paths first. And how many of those possible paths are there? Well, counting those is complicated on this graph.
49.
Sorry, say that again.
I think it's 49 because we got 50. So there's one square, or so should be 49 ways of going back and forth.
That's a good thought. Don't forget though that we want to divide by 8. So if we work backwards from what we think the solution is, that would be 50 minus the number of squares times 8, right? So it would be 42. So there's probably 42 different ways to start at each one of these individual nodes and take 4 steps and get back there. There are probably 42 ways to do that that are not involved in this square. Let's see, can I reconstruct that 42 very quickly? We have 5 edges on this, right? So for each one of those edges, let's see, not quite. So you need to do the first edge would be yeah, let's see. That would be 9 plus 9 plus 4 plus 4. It's 26. That's not quite right yet. Oh, because there's also oh no, yeah. I thought I knew how to do this, but my numbers are coming up wrong. So I'll have to double check. But if you account for the number of 2-step paths here that are not squares, in theory, you can do it. Yes. Did you get a photo of this? Of the 8 to the 4th? So the 5 cycle would have the same problem. The problem is you have to account for the shorter paths that go through things. So in the case of the 5 cycle, you might pass through a triangle and then one edge and back, for example, and that would be even more interesting and complicated. All right, let's see. We're only about 2/3 of the way through this set of slides, and we've only got about 5 minutes left in our official time slot here. So in fact, we are going to continue this on Monday, although I'd hope to get a little bit farther through this on Monday because there are other things I want to today because there are other things I want to talk about on Monday. Talking about the Markov processes. Let's see. So go back to sharing my screen here. I share the right screen? Yes. All right, so with the 4 cycle, well, you can alternate the oh, that's the ones I forgot to take into account there. So the alternating between 2 paths, the A there, but also you can also go 2 hops out in any direction and back, and that will that's also possible. So on this arbitrary graph, you could go well, let's see, that what's written there doesn't actually match that, but you could go ABC BA on particular graphs, and actually that would actually work on the graph that I drew here on the screen or on the whiteboard. So this tells you how long it might take you to get back to where you started from various things. All right, so returning to the issue of social graphs, we can do the same thing for the social graph. We looked at this. If we write this out, how big a matrix are we going to end up with if we write out this whole thing? If there were 1 billion people on our social network, and you write out the adjacency graph of everybody who's friends, how big is that adjacency graph? Mortistel, what do you think? If we have 1 billion people in our social graph, how big is our adjacency matrix?
How big?
Yeah, how big is the adjacency matrix for 1 billion people?
I can't imagine. I can.
Well, it would be 1 billion rows and 1 billion columns, right? It would be a
Yeah.
1 billion by 1 billion matrix. So that would be 10 to the 18, right? That's how big a graph we're talking about if you want to do the whole social graph for Facebook. And Facebook's actually bigger than 1 billion people, so it's going to be bigger than that. But 10 to the 18 entries, 10 to the 18 bits, give or take 10 to the 17 bytes. That's a lot of bytes, even if you just keep it as bits. Man, that's a lot of data. All right, so one of the things that we can talk about. So we asserted here earlier that the shortest path between any two people, the biggest shortest path is, or longest shortest path is 6 people. That there's never at least 7 hops between any two people. So that concept is what we would call the maximum degree of separation, or in graph theory terms, it's what we call the diameter of the graph. And in this particular graph that's here, the longest shortest connection between two nodes is from C to F, and that's 3 hops in this case. So the diameter of this graph is 3. Of course, if you really wanted to make a longer path between C and F, you could do that. You could go C, A, B, D, F and make a longer path, but that's not what we're talking about. We're talking about the shortest path between two nodes, and the shortest path between C and F is 3. So when you talk about the diameter of the graph, you take all possible pairs, you compare all of the nodes, and look for the longest one of those shortest paths. All right, let's see. So if we do this, the assertion is that if everybody is connected by a graph of less than by 6 or fewer steps in this, that if we took not the Facebook graph, but the friends graph of everybody on the entire planet, all 7 billion people on the planet, almost 8 billion people. If you took that entire adjacency matrix and took the 6th power of that, then every entry in that graph would be non-zero, because the zeros are ones where we have not yet found a path. Right? So that's the basic idea there. And that takes us to graph isomorphism, and we'll pick up with graph isomorphism on Monday. So I'll see you all on Monday. Any comments, questions before we wind up? All right, if not, I'll see you all regular time and place on Monday, and we'll pick up from there. Stay safe, y'all.